Tokens are the one thing the model actually sees. They decide whether your AI system is cheap or reliable or expensive and broken. I've shipped systems processing a lot of tokens. I've done AI engineering work on projects involving Apple, Amazon, Netflix, and Meta. I've watched strong engineers light money on fire, ship apps that randomly break, and blame the model. The real problem? They never understood the one thing the model actually sees: tokens. The model works with tokens, not words, not sentences. Almost nobody building it with AI understands how tokens really work. The gap is why the same problems keep repeating. I'm going to cover how tokens work with real numbers and the parts that almost never get explained. By the end, understand why prompts fail, bills are high, responses are lag, and why models can't count the letters in strawberry. Stage 1, what a token is. Stage 2, how text gets tokenized. Stage 3, how the model uses tokens. Stage 4, the context window on cost. Stage 5, cost, speed, reliability. None of this requires deriving math or training a model. Everything that decides how a real AI system behaves is an engineering decision sitting on top of the model. That's the layer we're going to live in. The biggest mistake people make is assuming the model reads their words. It doesn't, ever. You type English, the model doesn't see English. It sees numbers. Before a single thing happens, your text gets chopped into tokens. Each token gets a numeric ID. The model only ever works with those IDs. Hello world tokens equals hello plus world. Those are IDs 15496 plus 1917, for example. You think in words, the model thinks in tokens. That gap is the source of most confusing failures. The whole job is closing that gap. A token is a chunk of text, not a whole word, not a single letter. Rule of thumb, it's about 4 characters or about 0.75 of a word in English. Common words like the and are a single token each. A rare word like anti-disestablishment Aryanism gets split into 5 or 6 pieces. The more common something is in the language, the cheaper it is to represent. Spaces count. Punctuation counts. Even capitalization can tokenize differently. Hello, ID 9906, and hello with a leading space, ID 24748, are literally different inputs. Same letters to you, different tokens to the model. Numbers don't arrive as values. They get chunked. For example, 1, 2, 3, 4, 5, 6, 7 gets broken up into 1, 2, 3, then 4, 5, 6, and then 7. The model never sees the quantity. It sees fragments. This is a big reason why models fumble arithmetically and miscount digits. Every bracket, every level of indentation, every new line is its own token or two. The same logic written densely can cost far fewer tokens than when it's heavily nested. If you're sending large code bases to a model, the formatting alone is part of your bill. Every model family has its own tokenizer and its own vocabulary. The same sentence can be different number of tokens on one model versus another. When comparing prices, the per token rate is only half the picture. Also compare how many tokens each model actually uses for your next text. The tokenizer has a fixed vocabulary, usually about like 50,000 to a couple 100,000 tokens. It can't invent new ones on the fly. Everything you type has to be built from that fixed set. Common fragments like the, ing, sh are in the vocabulary where stuff gets pieced together. This process is called byte pair encoding. It starts with single characters, find the pair that appears most often, and merges them into a new token. Then it does it again thousands of times. The most common patterns become whole tokens. Rare stuff stays in small pieces. The word there starts as single characters, the letters T, H, E, R, E. Then they're merged into TH, then THE, then RE. Final single token will be THERE. A common word collapses to a single token after enough merges. Vocabulary is shaped by frequency in the training data. A common word gets one clean token, for example, like information. A rare word gets stitched from pieces like cryo, gen, and so cryogenically, for example. The tokenizer can always fall back to raw bytes. There's no word it can't handle. Rare things are just handled badly, split into many tiny pieces. Nothing breaks, it only gets expensive. That's the quiet cost of niche jargon, unusual names, and weird formatting. English is cheap because training data was English heavy. The same sentence, English, for example, that could be like 9 tokens. Hindi could be 20 tokens. Japanese could be 25 tokens. Billing for non-English users costs 2 to 3 times more per message. The same feature has completely different unit economics depending on the language it runs in. Almost nobody accounts for this until the invoice enforces them to. Some tokens exist in the vocabulary but barely appear in the model's actual training. The model has almost no idea what they mean. Feed one in and you get bizarre broken output. The most famous one was a forum user that ended up as a single token. The tokenizer and the model are 2 separate things that don't always agree. Quick aside, if working at this level is what you want to get paid for, that's exactly what I train developers for inside AI Engineer Launch. I teach the full AI engineering path, and I've got recruiters working round the clock to put my people in front of the right opportunities and land that first AI role. The link's in the description if that's you. Back to it. The model does exactly one thing: predict the next token. That's the entire engine. Everything that feels like reasoning is built out of that one move, repeated. First step, each token ID is converted to a vector, a long list of numbers. That vector is the model's real representation of the token, where meaning starts to live. Every token gets vectorized before any thinking happens. That's the bridge between the text and math. When it predicts the next token, it isn't choosing from a short list. It produces a score for every single token in the vocabulary. 50K, 100K, more. Anything more than that as well. Like it has a score for every one of those. It turns those scores into probabilities and picks one. It runs that process every token it writes. It looks at everything so far, scores every option, picks one, adds it, then repeats with the new token included. For example, the cat sat on the blank. So now out of the tokens, it gives a percentage. For example, it could say mat 62%, floor 16%, couch 11%, roof 5%. One token at a time in a straight line all the way to the end of the answer. Low temperature almost always takes most likely token and then consistent and repeatable output. So high temperature takes more chances. So basically more variety, more risk. Same model, very different behavior. Decided right here at the token level. Even at the lowest temperature, you won't always get byte for byte the same answer. Hardware math variation, basically. So if your test assumes the model is perfectly deterministic, they will flake for reasons that have nothing to do with your code. So, and the things you have to do is basically to design around it and don't fight it, because you're not always going to get, you put in this input, you could always get a deterministic, the exact same output every single time. So you have to design with that in mind. Because the model sees chunks and not characters, it gets how many R's in strawberry wrong. Basically, it will say like 2, but the correct answer is 3 because it looks like chunks. This is probably one of the most famous bugs in AI at the moment, at least. Strawberry arrives at, like, if you break down the word strawberry, it's like you have STR as one token, then AW as another token, then BERRY as another token. It never saw individual letters when it's broken down in this method. So the model isn't stupid. It's working with chunks where you assume it was working with letters as opposed to just groups of letters or chunks. So you see STRAWBERRY. However, the model sees STR as one chunk, then it sees AW as another chunk, then it sees BERRY as another chunk. That one idea explains a whole family of failures people blame the model on. Now, when you start counting letters, reversing a word, spelling backwards, strict rhyming, splitting on exact characters, that's where you see things kind of like vary. So anything that depends on individual letters is hard. The model was never looking at letters, at least the way it's designed at the moment. So now let's look at stage 4 of this, the context window. This is where most of the cost and speed actually comes from. Most people think of it as a memory limit. It works more like a token budget. Input tokens and output tokens all have to fit inside one number. The prompt, the history, and the answer all spending from the same budget. They're all the same pool of it. Context windows are huge now. 1 million tokens on some models, not just small, just models, right? That is not an invitation to fill them. Everything I put in the window, I pay for on every call, and it slows down the model down as it goes. The real skill is using little of the window as the task honestly needs. Prefill, basically reading, the model reads the whole prompt in one parallel pass. This is fast. Now decoding, which is the writing part, the model can only generate one token at a time, each depending on the one before. So this is slow. This is fundamentally asymmetric. This basically is asymmetry behind all the speed and cost that concerns. And this is why you see that the longer if you ever work with LLM, you will see that after a while, it will say like consolidating the conversation, because the longer the conversation goes, it becomes more expensive because it takes everything and then puts it back in there, and it's a slow context at that point. Input got read all at once. Output has to rebuild one token at a time. There is no way to skip ahead. Reading is parallel. Writing is a single fine line the model has to walk to the end. That's the real reason output costs more than input, and why long answers feel so much slower than long prods. The model compares every token to every other token. Double the context and you don't double the work. You roughly quadruple it, because it scales with the square of the length. A double context doesn't just cost more tokens, it costs more compute on every single one of them. To avoid redoing all the work on every new token, the model stores what it already computed to the KV cache. That cache grows with the context length. Longer conversations take more memory and get slower. This is why long chat can start to feel sluggish near the end. Models pay the most attention to the start and the end of a long context. things buried in the middle get missed. Stuffing the window can make response worse and more expensive at the same time. Less, but well chosen, will always and usually I would say wins. Pricing per 1 million token as of, I would say, like June 2026 would be like ChatGPT 5.4 mini. That's about 75 cents. That's coming in at about $4.50 coming out. Claude Sonnet 4.6 right now is about $3 coming in, about $15 coming out. Claude Opus 4.8, that's about $5 coming in, $25 coming out. And GPT 5.5, that's $5 coming in, about $30 coming out. The spread between a small model and a frontier one is the single biggest lever you could basically have right now. Monthly cost, input tokens over like 1 million times the input price plus output tokens over 1 million times the output price. It's basically a simple formula. The trouble starts when those token counts get really, really big. Reasoning models generate hidden tokens while they work through a problem. I never see those tokens, but I pay for them as output. A response that shows 500 tokens can actually cost 2,000 tokens built. When a reasoning model bill looks too high, this is usually the reason. A bloated system prompt is a per call tax paid for the life of the feature. It feels free because I wrote it once, but every user, every call, every day, I'm paying to send it again. Audit and trim system prompts regularly. Stuffing 20 few shots examples when 3 would do is burning tokens on every call at scale. Examples are one of the most powerful tools I have. They're also one of the most expensive. So use the fewest that still get the job done. If the start of a prompt stays the same across calls, the model can reuse the work it already did. Cache input runs up to 90% cheaper. So key rule here, put stable part at the front, the part that changes at the end. If the work doesn't need an instant answer, send it in a batch and read it asynchronously for at half the price. So use cases, overnight reports, bulk processing, evaluation, back office jobs. Same tokens 50% off purely for being willing to wait for it. In a long conversation, I don't have to keep resending the entire history forever. Summarize what happened earlier into a short recap and drop the raw transcript. The model keeps the thread and I stop paying for the same 50 messages on every single turn. That one habit changes the cost curve of any chat product. RAG pulls back document chunks and stuffs them into the prompt before the model even sees the question. Pull top 10 chunks instead of top 3 and just triple the input tokens on every query. The retrieval settings most people never touch are a line item on every single request. Every tool I give an agent is described in tokens and rides along on every call. The agent loops, calls tools, calls other agents. Each step pays for the full context again. This is why a slick agent demo can cost 10 times more once it's actually running, often 3 to 10 times the prototype estimate. Page 5. What controlling the token layer actually buys. It comes down to 3 things. 1. Cost. 2. Speed. 3. Reliability. Tighter prompts directly equal a lower bill. I've seen teams cut their token spend in half just by trimming bloated prompts and system messages nobody ever audited. The model didn't change. The discipline. Stop thinking in cost per token. Think in cost per task. A cheap model that needs 5 tries can cost more than an expensive model that nails it once. The real number is dollars per successful outcome. That shift alone changes which model to reach for, basically. Output is the expensive slow half, so ask for less of it. Tell the model to be concise, return only what's needed, cap the max tokens. Half the latency and a real chunk of the bill can disappear from that one habit. Embedding text for search is dirt cheap compared to generating a large model. A lot of AI work is really retrieval and classification that barely touches the expensive models. Knowing which jobs are cheap and which are expensive is half the craft. Send simple high-volume work to a cheap model. Save the frontier model for the few tasks that truly need it. Done well, this alone can cut a bill by basically 5x to 20x with users never noticing a difference. The single biggest lever available. These levers multiply together. Route cheaper plus cache the stable prefix plus batch what can wait plus trim the prompt plus shorten the output. Each one is a multiplier on its own. Used together, they multiply against each other. This is how a frightening bill turns back into a reasonable one without touching the product. I worked with a company that started around $20 a month with just a few employees on an LLM. They rolled it out to 2,000 people. Watch what happens to that number. 2,000 employees times 10 prompts per day times 22 days, 2,000 over 1,000 out tokens. Monthly cost is, let's say, again, we did use multiple models here, but let's just show you per model. GPT 5.4 mini, that's $22,640. Claude Sonnet 4.6, $9,240. And then Claude Opus 4.8, that's $15,400. And ChatGPT 5.5, that's $17,600. So now 2,000 employees times 25 pounds per day times 22 days, that's 4,000 in, 4,000 in, 2,000 out for tokens. Monthly cost, GPT 5.4 mini is $13,000, $13,200. Claude Sonnet 4.6 is $46,200. Claude Opus 5.8, that's $77,000. And ChatGPT or GPT 5.5, that's $88,000. So now if we compare more heavy usage here, so 2,000 employees times 50 prompts per day times 22 days, that is 10,000 in, 4,000 out. The documents, regs, agents added, these are the tokens you're using for it. So monthly cost, GPT 5.4 mini, that's $56,100. Claude Sonnet 4.6 is $198,000. Claude Opus 4.8, that's $330,000. And GPT 5.5, that's $374,000. Same company that started at $20 a month. And that's the reality. This is why you hear all the news. This is that companies are blown away by the cost prices, not what they projected. So if you can see here, the line doesn't climb gently. It bends and takes off. It's exponential here. Token usage compounds as people lean on the system more. This is how a $20 pilot turns into a six-figure invoice. Token prices dropped approximately 98%, but enterprise bills climbed 320% because usage exploded. That exploded there. So one company ran up about $500 million single month AI bill after forgetting to set a use limit. Uber burned through its entire AI coding budget for the year by April. 73% of enterprises say AI costs came in way over projection here. Average enterprise AI budget jumped from 1.2 million to 7 million between 2024 and 2026. Everything I just showed is only the token bill. It doesn't include web search, file processing, vector databases, infrastructure, monitoring, security, agent runtime, or engineering time. The total real cost is much higher. I can't fix what I can't see. Tag every API call by feature, team, and workflow. Token spend without attribution means a surprise invoice with no idea where it came from. Example breakdown, let's say a chatbot, 40%, agents, 45%, search, 15%. I can cut what I can measure. Because the model writes one token at a time, the length of the answer is usually what decides how long the user waits. A 500 token reply takes roughly 5x as long as a 100 token reply. If an app feels slow, look at the output length before touching the code. TTFT, time to first token. How long before anything appears? Tokens per second, TPS. How fast it streams after that. A model can be strong on one and weak on the other. Measure both, not a vague sense of fast or slow. Stream the output as it generates. The user sees movement almost immediately instead of starting at a spinner. Total time is identical. The experience is completely different. An easy win that costs nothing. A surprising share of so-called random failures are really token problems. Weird formatting, trailing spaces, inconsistent casing, or asking for character level work the model physically can't see. Fix that token layer, and a lot of that flakiness simply stops. Instead of hoping for clean JSON, force a schema. The model can only return valid structured output. Set stop sequences and a hard token limit so it can't run off the rails. Most shaky pipelines they basically get stable the moment you constrain the output. Yearly evaluations that score cost, latency, and quality on real examples. When I change a prompt or swap a model, I know whether it actually got better or just different. The engineers who measure are the ones who keep improving instead of guessing. Every major tokenizer is something you can inspect directly. Paste in a prompt and watch it split. Summarize the report in 3 lines, 7 words, 8 tokens. The first time you do that on a real prompt, the bill stops being a mystery and starts being something you can control. None of this requires a new model architecture, a training run, or any proofs. Everything that decided cost, speed, and reliability has an engineering decision sitting on top of the model. Which model to use, how the prompt is built, what gets cached, how retrieval is tuned. Research invents the model. Engineering makes it work in the real world on the budget, at scale. Different jobs, engineering does not require a PhD. It requires knowing exactly what just walked through. The skills that matter most here are not exotic. Thinking in systems, caring about cost and reliability, knowing where the bottleneck is. The AI part sits on top of skills strong engineers already have. It doesn't replace them. The people who do this best almost always came from somewhere else first. Day-to-day orchestration, wiring models together with tools, retrieval, and memory. The stack, LangChain, vector databases, RAG, agents, evaluation, monitoring. It looks far more like building and running a system than writing a research paper. What every company is actually buying comes down to one thing: someone who can take a model that's powerful but expensive and unpredictable and turn it into a system that's cheap enough to run, fast enough to use, and reliable enough to trust. That's the whole job. And the token layer is where it's won or lost. The engineers who understands the token layer are the ones who can shift AI that is cheap, fast, and reliable. Right now, those are exactly the engineers companies are competing for right now to hire. If that's the engineer you want to become, that's the whole reason I built AI Engineer Launch. I train developers in the real AI engineering stack, the things companies are actually hiring for. Recruiters working round the clock to get my people in front of the right opportunities. Link is in the description.